Hi, my name is Thomas Miko, and in this video we will explore how computers and their peripherals communicate from USB to Thunderbolt. From assembling computers out of parts to simply plugging in a keyboard, most people know that computers have wires running through and connecting different components. But what are these wires actually doing? Well, to put it simply, individual parts of a computer don't always know what the other parts are doing or what information they have to share. To solve this, computer architects created protocols for how to generate electrical signals that individual parts of a computer can use to communicate with each other. By following these protocols, the individual parts of a computer are, in a sense, speaking the same language. Because of this common language, the majority of electronics that you can buy in a store can simply be plugged in directly to your computer and work immediately, without needing to do any programming on your own end. One of the most common of these languages that the average person uses is called the USB protocol, which stands for Universal Serial Bus. As the name implies, the point of USB is that the language is universal, and in the modern day, this is achieved, as all personal computers that can be purchased already have the connectors for USB built in, and already understand the protocol without you needing to do any work. The other part of the name to understand in USB is serial bus. All this means is that the data going through the wire happens one piece of information at a time. For a computer, which communicates using ones and zeros, this means that the electrical signal in the wire is either on or off. So let's take a look inside a USB 2.0 cable, where you might be surprised to see 4 smaller wires, not one. The reason for this is actually pretty simple. First, 2 of the 4 wires are just to deliver electricity to whatever is connected, which commonly in electronics requires separate wires for 5 volts and for ground. But we still have 2 more wires, called data plus and data minus, just to send one piece of information at a time. Well, to understand why USB needs 2 wires to send one signal, we need to look at the signals generated from a USB cable. Here, in this example, the top blue line is the signal for the data plus wire, and the bottom purple line is the signal for the data minus wire. When the signal moves up, that means there's electricity flowing through the wire, and when it goes down, the electricity is off. And pretty quickly, after looking at it, you may notice that the two lines are opposite to each other. When the top line goes up, the bottom line goes down, and vice versa. Well, if we look at the datasheet for the USB 2.0 cable, you can find that these ups and downs mean ones and zeros. The first row means that when data plus goes up and data minus goes down, the data being communicated is a 1. And conversely, when data plus goes low and data minus goes up, the data being communicated is a 0. But so far, it isn't clear why we need 2 signals for one piece of information. Well, if we look at more of the signal, we can see that the pattern doesn't always continue. To understand this example, we can look back at the datasheet. Here, we can see an example of an end-of-packet signal. This just means that whatever piece of information we are sending across the cable is done being sent. We can understand what this signal means by again looking at the datasheet and seeing that the end-of-packet signal is defined by both data plus and data minus being low. By looking further into the datasheet, it becomes more apparent why the USB cable needs more than one wire just to send one piece of information at a time. Even though the two components communicating with USB only need to send a 1 or a 0 at a time, it also needs to communicate more information, like when the data is starting or ending. So by using 2 wires, the components can change each line to communicate with the information as needed. Now that we understand USB 2.0, let's take a look at a more modern and much faster version called USB 3.0. 3.0 has the wires that we just got familiar with from USB 2.0. We see the power and ground wires along with the data plus and data minus, all on the top row. But now we have a second row containing 5 more pins. One of these pins is just another ground for the electrical connections, but the other 4 are 2 more sets to communicate data. So now we have 3 total sets of data lines to communicate between the 2 devices. But because USB 3.0 uses all the pins USB 2.0 uses, a device that was made to use USB 3.0 can still use the older 2.0 cable with reduced efficiency. With these new sets of wires, USB 3.0 has a theoretical maximum speed of 5,000 megabytes per second compared to the 480 megabytes from USB 2.0. Another recent innovation coming with USB 3.0 is called USB-C, which among other uses solves the biggest issue the average person has with a USB cable, not being able to plug it in on the first time. So let's take a look at USB-C, which is compatible with the USB 3.0 protocol, which at first may be confusing, because USB-C looks like it has over twice as many connectors as the USB 3.0 cable we just saw. However, by taking a closer look at the names, you may notice that the top and bottom connectors are just mirrored versions of the same pin. So the total wires actually in the cable is not 24, but actually 12. And of these 12, the majority are the same cable as 8 of the wires seen in a normal USB 3.0 cable. And 2 of the remaining 4 new wires are just renaming the power pin for the 5 volt and adding a second one. The only 2 new wires we haven't seen before are the ones labeled CC and SBU. These 2 pins are used to help 2 connected devices communicate what the cable is meant to be doing. First, the SBU pin is used to deliver a small amount of information on what kind of information is being sent between the 2 devices, if any. Next, the CC pins are helpful to determine whether the cable is plugged in a flipped or unflipped way. When someone plugs in a USB-C cable, there are only 2 orientations that the cable can be plugged in. However, you are not expected to know which orientation would be correct or incorrect. So to solve this, the cable is designed for there to be no incorrect orientation to plug in the cable. That leaves work for the computer to try and figure it out on its own. To understand how this is done, let's take a look at this diagram made by Microchip Technologies, explaining how the CC1 and CC2 pins can be used. Here, we see the 2 possible orientations for the cable, unflipped and flipped. In the first case, electricity is flowing between CC1 of the connected device to CC1 of the computer. This is the unflipped case, because electricity is flowing between pins of the same name. However, in the flipped case, we can see that CC2 is connected to CC1. When this happens, the computer will detect the cable is in a sense flipped. In both of these cases, the cable is expected to work as normal, and as far as the user knows, there is no difference. But to the computer, it uses this information to know which set of connectors to use when sending data, either the top or the bottom. Finally, let's understand what USB-C can do that previous USB versions couldn't. Because of the high speeds that USB-C is now capable of, computer designers have begun to implement it in new ways that allow it to replace other cables that were previously dedicated to one purpose. One of the uses USB-C is now commonly used for is for delivering power to devices like phones or laptops. While using USB as a charger is not a new idea, the amount of wattage that USB-C can deliver has allowed it to be more common for larger devices. Previously, USB 2.0 was able to provide a maximum of 2.5 watts when delivering power to a device, but now USB-C can be used to deliver up to 240 watts of power, following the USB power delivery guidelines. Additionally, with the higher capability that USB-C has to send data, designers have been creating adapters that allow display information to be communicated over a USB-C cable. This data has historically needed a dedicated cable type to support the large amount of information going from computer to monitor at high speeds. All this brings us to Thunderbolt, which allows computers and connected devices to fully utilize the power inside the USB-C cable. Thunderbolt is not a cable, but instead a port designed to use the same pins and layout as a USB-C cable, but with a different controller inside the computer. Similar to how USB 3.0 is compatible with USB 2.0, Thunderbolt can connect to devices that use USB-C, but Thunderbolt ports are not required to use the USB 3.0 protocol. They are capable of using protocols like its own of the same name, or one for video called DisplayPort. Additionally, Thunderbolt is designed to use a protocol that normally is used for connections inside the computer, which allows for much higher speeds. For example, Thunderbolt allows the computer to use PCI Express to talk to external devices, despite historically this protocol being used for fast communication between a computer's processor and its storage or graphics devices. By doing this, a Thunderbolt connection is much better at transferring data or display information than would normally be achieved with a standard USB connection. To dive deeper into the information behind this video, check out these sources, or find the original slides used in this video in the video description.